It's visible. Yes.
Okay.
Maybe we'll just wait for a few minutes for the people here to show up.
Yeah, no problem. Yeah.
Yeah, thanks.
Jeevan. Hello.
Hi. Hi.
How are you doing?
Sorry, I can't hear you clearly.
How are you doing?
Yeah, I'm doing good. How are you?
Okay. Thanks for waking up so early to do this.
Yeah, no problem.
We're just waiting for a few more people and then we'll start in a few minutes.
Yeah, no problem. Yeah.
Okay, maybe we can get started. Yeah, we're very happy to have Jeevan Chandra today, who's going to tell us about the thin shell line defect correspondence. Yeah, Jeevan, you can start.
Okay, great. Thanks a lot for the invitation to give a talk at ICTS. So the title of my talk is the thin shell line defect correspondence, and it is mostly based on this first reference in collaboration with Tom Hartman and Viraj Merulia. And also towards the end, I might talk a little bit about this other paper. Okay, so let me start by giving some extended motivation about wormholes and statistics in case people are not familiar with it. So I should mention that you should feel free to stop me at any point and ask questions. Um, okay, so gravity as a low energy effective field theory captures statistical information about the quantum theory in the UV. And the most famous example of this is the black hole entropy, which says that the entropy of the black hole is given by its area in Planck units. and it informs us about the coarse-grained density of states of the underlying quantum theory at high energies. In recent years, higher topology contributions to the gravitational path integral called Euclidean wormholes have been shown to capture more refined statistics of the quantum theory in the UV. So these Euclidean wormholes are connected bulk geometries that are joining disconnected boundary components. So here is a rough picture of a wormhole where the boundaries are circles. There are n boundaries corresponding to n circles. And the wormhole is a connected contribution in the bulk theory. So wormholes are interesting for several reasons because they have been recently shown to calculate the entropy of Hawking radiation and thereby reproduce a page curve that is consistent with unitarity. So for our purposes, we are interested in wormholes because they they carry signatures of quantum chaos and quantum gravity. To give some examples of this, we recall that the double trumpet wormhole in JT gravity or the double cone wormhole in general dimensions calculates the linear ramp in the spectral form factor, thereby showing that gravity realizes the random matrix universality. And more recently, it has been shown that wormholes supported by matter world lines calculate statistics of OPE data of CFTs, thereby showing that gravity realizes the eigenstate thermalization hypothesis. Since random matrix universality and eigenstate thermalization hypothesis are two signatures of quantum chaos, I would say we can use wormholes to capture the signatures of quantum chaos. So let me explain very briefly about these two aspects of wormholes. So recall that the double trumpet wormhole in JT gravity is this topology, which is topologically a cylinder with boundary lengths, renormalized lengths of the boundaries being beta 1 and beta 2. So the path integral of JT gravity on this topology can be evaluated exactly, and it takes this particularly simple form. And from this expression, you can see that if you analytically continue the boundary lengths to complex values, you get a linear ramp in the connected spectral form factor at late times. So specifically, I'm analytically continuing the temperatures to be beta 1 equals beta minus plus IT and beta 2 is beta minus IT. And with these boundary lengths, the wormhole gives a contribution to the connected spectral form factor. And from this expression on the right-hand side, you can see that at late times, it gives you a contribution which is linear in time. And this is equivalent to the 2-point function between the energy of between the density of states taking this particular form, particular universal form, which is predicted by random matrix theory. So the upshot is that off-shell wormhole topologies in JT gravity have knowledge of spectral statistics of random matrix Hamiltonians. So this feature also seems to be true in 3D gravity. Because there is Kotler and Jensen showed that the spectral statistics of 2D CFTs can be captured using this double torus wormhole. So this wormhole is like a generalization of the double trumpet because the circular boundaries in JT are turned into torus boundaries in 3D. So this again is a contribution to the 2-point function of the partition function of CFTs. And if I again continue the boundary temperatures to Lorentzian times, I get a linear ramp. Okay, so the lesson seems to generalize to higher dimensions. So optional wormholes in 3D gravity seem to encode spectral statistics of 2D CFTs. But we know that since 2D CFTs are characterized by the spectrum and the OPE coefficients of local operators, so the natural question that we can ask is what three-dimensional geometries encode OPE statistics of 2D CFTs? Okay, so before discussing about wormholes, so let me first describe that OPE coefficients of 2D CFTs have universal asymptotics. Particularly, I want to review the derivation of the Cardy formula for OPE coefficients of local operators in 2D CFTs. Okay, so it has been shown by a number of papers starting in 2016 that the OP coefficients of Virasoro primaries in 2D CFTs have universal asymptotics, meaning that the square of the OP coefficients for sufficiently heavy operators is given by a smooth function of conformal weights. The function is denoted C0. So for purposes of this talk, the explicit form of C0 is not important. So I will not be writing down the form of C0, but it's a function which is known in closed form. And these asymptotics are valid for any CFT, any irrational CFT with central charge greater than 1, when at least one of the operators is taken to be sufficiently heavy. And by sufficiently heavy, I mean the operator weights are very large in comparison to the central charge. So the important property that C0 satisfies is it's a fusion kernel or the Virasoro crossing kernel, which basically transforms the identity block in one channel and expands it using dual channel blocks. And so in this sense, it's a fusion kernel. So this fact is going to be important for our purpose because we are going to generalize this idea to a class of line defects later. This is an important fact to remember. And another interesting
Yeah,
sorry.
So here you're just writing the holomorphic part, right?
Yeah. So this is the holomorphic identity block, the Carroll identity block.
Okay. Yeah. And this rho naught h is the same
is the Cardy density of states.
Okay. The full thing or just the exponential part?
It's the exactancy expression. So this expression, that fusion transformation law that I've written, is exactancy.
No, I meant this rho naught of h. Sometimes people just write it as a pure exponential, and sometimes it's written as some more complete function, right? Like say,
well, I mean, it's not a pure exponential because, well, I can write down the expression. It's like up to numerical factors. It's like sinh 2 pi pv sinh 2 pi p over b, where p is like p is a proxy for the conformal weights. So in the limit that the central charge or this parameter b goes to 0, it reduces to the usual exponential form that we are familiar with.
Right. Yeah, that's what I was asking. Yeah.
Yeah. Okay. So.
Jeevan,
yeah.
Could you perhaps also elaborate what the overline in the first formula here is, like the average over Cijk squared?
Okay. So the average here is just the necessary amount of coarse graining required to make sense of this expression, because we know that the operator spectrum in a compact CFT is discrete. But on the right hand side, I have a smooth function of conformal weights, whereas on the left hand side, without the overline, it's just the OP coefficient of 3 operators. So in order to make sense of this expression, you need to do some amount of microcanonical averaging. meaning that you average over a small window around these weights centered around the operators I, j, and k.
Okay. Yeah.
Following up on that,
Yeah.
so for this Cardy density, people like Sridhar Pal and others have proved these Tauberian theorems.
Yeah, correct.
Put some precise size on the window and make the nature of the averaging precise. Is something similar known for thisCijk square?
As far as I know, I don't think people have written down this have done the Tauberian analysis very carefully for the case of the OP coefficients. Yeah,
Okay.
I think there's a much better analysis done for the density of states and but not for the OP coefficient. So I think it's a interesting thing to think about. I mean, worry about the size of the averaging window and do the Tauberian analysis more systematically for the OP.
Yeah, okay.
Okay, so another important fact is that up to normalization, this formula C0 is proportional to the diversity structure constants in Liouville CFT. So diversity structure constants are nothing but the expressions for the OP coefficients of local operators in Liouville CFT. So this plays a crucial role in reproducing C0 from 3D gravity. I should mention that this formula, this Cardy-like formula, is not applicable for Liouville CFT. Because Liouville CFT is a non-compact CFT. So we don't expect this Cardy-like asymptotics to hold for Liouville CFT, and so this is as such is a surprising fact that that C0 is proportional to the diversity structure constants. Okay, so what does this Cardy formula buy us? So for chaotic CFTs, this Cardy formula for the OP coefficients offers a generalization of ETH, which is consistent with Virasoro symmetry. So recall that ETH is a statement that the matrix elements of few body operators.
Sorry, Jeevan, just about your previous comment.
Yeah.
You need the compactness because in some kind of Cardy formulas, you need the ground state to be isolated, and there should be
Exactly.
something.
Exactly. So you would want a normalizable vacuum state because the derivation of this Cardy formula you see has relies on the identity block.
Yeah.
But Liouville CFT does not even have a normalizable vacuum state. Yeah, it's you can't make sense of these expressions in Liouville CFT.
Yeah, okay.
Yeah. Okay, so ETH is a statement that the matrix elements of few body operators between heavy energy eigenstates has this following form, where F and G are smooth functions of energies, and F depends on the average energy, whereas G depends on the difference in energies. And so the important part will be this will be the off diagonal piece. So where Rij is a random matrix, which is Gaussian to leading order. So this is like the noise term in the ETH, and we are going to use wormholes to extract this noise term, extract the moments of this noise term. Okay, so as I said, the Cardy formula for the OP coefficients is a generalization of ETH and sometimes called the Virasoro ETH. So Virasoro ETH is a statement that the OP coefficients of light and heavy operators in various regimes have Gaussian statistics to leading order at large value of the dimension of the heavy operator. By Gaussian statistics, I just mean that their variance is given by this expression C0. And these, so far, all the results that I've discussed apply for any C greater than 1 CFT. But there is an extended regime of validity for these asymptotics for holographic CFTs. So holographic CFTs have large central charge and sparse low-lying spectrum. And it's expected that these asymptotics are valid all the way down to the black hole threshold. So you should think of this statement in analogy with the usual Cardy formula having an extended regime of validity as shown by Hartmann, Keller, and Stoiker. So the Cardy formula for the density of states has been shown to be valid almost up to the black hole threshold. Okay, so the natural question that we want to ask is, how much does 3D gravity know about this universal dynamics of heavy operators in 2D CFT? In other words, we are asking the question of how is ETH reproduced from 3D gravity? So the most important relation that allows you to realize these asymptotics in 3D gravity is the fact that the partition function on this particular two-boundary wormhole reproduces this function C0 that we derived using bootstrap. Okay, so this wormhole has the topology of a thrice punctured sphere times an interval. So these dots denote local operator insertions. And these local operators, if they're below the black hole threshold, they source the world lengths of heavy point particles, which propagate from one boundary and to the other. So, basically, this wormhole reproduces this function C0, and so this is a two-boundary wormhole, and multi-boundary wormholes, like meaning two and more boundaries. So these wormholes compute higher moments of this OPE statistics. And this can be verified since the partition function of any multi-boundary wormhole can be computed exactly in central charge using the recently proposed Virasoro QFT prescription. For instance, consider this particular four-boundary wormhole where the boundaries are all four punctured spheres. And the world lengths of point particles travel cyclically between adjacent boundaries. So in this case, the partition function of this wormhole can be written exactly in central charge and takes this particular form. And importantly, this is also equal to the Gaussian average of the fourth power of the 4-point function. So let me say that this wormhole solves the boundary conditions corresponding to the product of four 4-point functions. So let's say I have an operator O1, O2, and again O1, O2. There are similar insertions on each of the boundaries. So this wormhole is a contribution to the 4-point functions, the fourth power of the 4-point function. And the observation is that it is equal to the Gaussian average of the fourth power of this 4-point function, because you can easily check that if you do the average, if you expand this 4-point function in some appropriate OPE channel, and then do the average over the OPE coefficients with the variance set by the function C0, you can reproduce this form, which is also equal to the partition function of this 4-boundary worm. And this is a check that works more generally. Like for any multi-boundary wormhole, it can be matched to the average of an observable in the average of multi-copy CFT observable.
you go back to the previous slide? I had a couple of questions.
Yeah.
So in this first point, I guess I have seen this a few times, but I didn't appreciate it till now. So these red lines are conical defects, right?
Yes, correct.
So all three of them are in some sense light. They are below the black hole threshold.
They are below the black hole threshold. Yeah.
So that means that gravity is predicting something even more than the bootstrap, right? Because in the bootstrap, you at least wanted to have one operator above the black hole threshold.
Well, that's true.
Okay, you're saying it's enough for the sum of them to be heavy or something?
Yeah,
or
exactly. Yeah. Because these are not like arbitrarily light. They're below the threshold, but they scale with the central charge. The operator weight scale with the central charge, and any two of these operators are heavy enough to create a black hole. Like you see, if I take any two of these operators, they can create a black hole. So in that sense, it's not that surprising that gravity is able to compute C0 in this different regime.
Well, even so, but the bootstrap argument you don't have, right? Like if you had all three operators being less than the black hole threshold, it seemed like the way you presented it, you don't have a bootstrap argument for this being equal to the C square.
Correct. Yeah. That's right.
Okay. And just to understand this point number 3, I don't think I quite got the fourth power of the 4-point function, and you have some averaging squared. And could you just unpack this formula a little bit? What on the right?
Yeah, sure. Yeah. Okay, so let me expand the 4-point function in an appropriate channel. So let's see. So the 4-point function, I can expand using OPE coefficients, C12P squared, where P is a label for all the primary operators in the spectrum of the 2D CFT, and then I have the conformal block. Okay, so this is the 4-point function expanded using this particular channel. Now I can consider the fourth power of this 4-point function. It's like I'm running out of space. Okay.
Right. So you'll get a sum over 4 P's, P1, P2, P3, P4.
Yeah, exactly. So I'll get a sum over 4 P's, like C, 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 and similarly there's corresponding C. I think there'll be 8 C. Sorry. So there'll be 8 such C's, right?
Is 4 holomorphic, 4 anti-holomorphic?
Correct, exactly. C's and C stars. And then when I take the average, I do a Wick contraction between these OP coefficients, and so the Wick contraction sets the variance to be C0, and
but somehow all the P1, P2, P3, P4 become a single number H.
Exactly. So because that's the assumption of Gaussian statistics. Because when I impose this variance, what I'm doing is the following. So suppose I have C12P and C12Q, and then I take the average. I would set it to be mod C0 squared delta PQ. So yeah, so I set the internal weights to be the same in all the copies.
I see.
Yeah. So that is the statement that these OP coefficients are Gaussian random.
Oh, this is a fully connected 4-point function.
Yes.
Okay.
Yeah.
Because I mean, naively, you would have thought there would be terms where two of the p's are equal to each other, and then the other two p's are equal to each other, but something else, right?
True. What you can do is you can do a saddle by saddle match, because there are different such contributions to the fourth power of the 4-point function. Like you can consider like partially connected contributions, and they would match with some other bulk geometries. So to match this particular connected four boundary wormhole, I want to do a Gaussian average where all the copies get connected.
Yeah. Okay. Thanks.
Yeah. Okay, so that was about the external motivation of the talk. So if there are any more questions, you can ask. Otherwise, I'll like go into the main part of the talk. Okay. So far we discussed that universal dynamics of local operators in 2D CFT are encoded by wormholes in 3D gravity. But we know that 2D CFTs could have extended operators like line defects. For example, like you could have conformal defects, like for instance, the famous Kondo defect, which is used to model impurities in physical systems. So the natural question that comes up is, do line defects also exhibit ETH-like statistics, which match with appropriate wormhole amplitudes in 3D gravity? So in this talk, I will describe a particular non-conformal line defect that sources a thin shell of dust particles in 3D gravity. And in particular, I will show that the matrix elements of this defect between high energy eigenstates is random with variance set by another smooth function of the weights. And M is like a mass parameter for the defect. So this is the non-conformal defect. So this is an analogous statement that generalizes the universality of OPE statistics of local operators to a class of line defects in CFT. So so this is a Cardy formula for line defects. Okay, so it turns out that we can derive the above Cardy formula by evaluating the structure constants of a corresponding line defect in Liouville CFT. So again, we are exploiting the fact that even for local operators, we observed that this C0 function was proportional to the DOCC structure constants. So similarly, there's such a correspondence even for extended operators. So we are going to utilize that to derive this expression for the Cardy formula. So again, as I mentioned, this is surprising at first glance because the Cardy formula is applicable only for compact CFTs with central charge greater than 1 and doesn't apply to Liouville CFT, which is non-compact. Okay, so I will show that these structure constants also govern the partition functions of black holes and wormholes sourced by thin shells of dust particles. And finally, I'll describe a precision test for these statistics by constructing wormholes using a domain wall solution. So if I have to like explain the plan of the talk using a simple diagram, so this will be the basic upshot of my talk. So this is the duality that I want to establish between thin shell black holes and wormholes in ADS3 and statistics of line defects in dual CFT2. And it turns out that to establish this duality, it is convenient to establish these two dualities. So you can reduce the calculation of the partition functions of appropriate black holes and wormholes to calculations of calculations in Liouville CFT. And also you can reduce the problem of finding statistics of line defects in dual CFT to the problem of finding the structure constants of line defects in Liouville CFT. Okay, so I'll get into more details now, but if you have any questions about the overview, you can ask. Okay. Okay, so as I mentioned, the important part in establishing this correspondence between thin shells and line defects is to use Liouville CFT with corresponding line defects. So recall that Liouville CFT is the theory of hyperbolic metrics on Riemann surfaces, and it's described by the following action, where phi is the Liouville field. And so it's roughly like a like a scalar field with an exponential potential. So this mu is a cosmological constant term. And B is known as the Liouville coupling. And the Liouville so this is a two-dimensional CFT. So this is a two-dimensional CFT. And so the central charge of this two-dimensional CFT is related to the coupling by this relation. So we'll mostly be interested in the limit b going to 0, which is equivalent to taking central charge to infinity. Okay, so for our purposes, we want to study the correlation functions of the non-conformal defect of mass m in Liouville CFT, which is an infinite product of local vertex operators. So in particular, we want to study the observables involving this line defect L sigma. So whenever I read L sigma, it refers to a line defect in Liouville CFT. Whenever I read D sigma, it refers to a line defect in a compact CFT. Okay, so this
Sigma is a one-dimensional curve.
Sorry?
Sigma is a one-dimensional curve.
Yes. Sigma is any one-dimensional curve on a Riemann surface. So this line defect is obtained by integrating the Liouville field around the curve sigma. And m is like a mass parameter of the defect. And this particular defect is can also be expressed as a continuous product of local vertex operators in Liouville CFT. So these are local vertex operators. And so this is the Liouville momentum, which is just a proxy for the weights of these operators.
Sorry, and capital R is like 2 pi r is the length of sigma or something?
Exactly. So let's say I put the defect on a circle of radius r. So r is like the radius of the defect. Okay. So the main goal is to extract the matrix elements of this defect in the semi-classical limit, that is in the limit b going to 0, by computing the classical Liouville actions on appropriate hyperbolic surfaces. Okay, so to do this, note that the classical Liouville action sourced by a line defect takes the following form. So what I've done is I've just inserted this line defect into the Liouville CFT path integral, and then I'm trying to understand like how does it deform the action of the theory. So the action of the theory gets deformed by the following source term. So this is a source term. So you could say that this Liouville solution is sourced by this non-conformal defect. Okay, so what are the solutions to this theory? So the equations of motion that you get by varying this action are the Liouville's equation, which is valid away from the defect, and a jump condition for the extrinsic curvature across the defect. So these are the equations of motion. So so this condition, that is the Liouville's equation, is equivalent to just requiring that the surfaces have constant negative curvature.
Sorry. Here we use capital phi, which is phi from Liouville theory, but rescaled by b squared.
Oh yeah,
Okay,
exactly.
okay,
Thanks for
okay.
pointing that out.
Mhm.
So when I write this small phi, it's the Liouville field that shows up in the exact path integral. Whereas when I write this bold-faced phi, it's rescaled by the Liouville coupling, and this is the combination that shows up in the classical Liouville action. Okay. So for our purposes, the solutions to these equations are hyperbolic surfaces that are constructed by gluing portions of hyperbolic disks to portions of hyperbolic cylinders. So this is how we are going to construct solutions. So all we are going to do is just glue the known solutions to Liouville theory, which are like the disk and the annulus solutions, and then we are just going to glue them together across defects. Okay, so just to illustrate some properties of this defect, so let's start with the simplest observable that can be computed using this defect. So the simplest,
Just to understand the notation. To understand the notation on the previous slide.
Yeah.
This capital K is the extrinsic curvature on sigma if the metric had been e to the capital phi.
Yes, it's the extrinsic curvature calculated with respect to the Liouville metric. So the Liouville metric can be parameterized in terms of the Liouville field by e to the phi mod dz squared.
Yeah.
So this is a metric with constant negative curvature. So in that metric, I'm calculating the extrinsic difference in extrinsic curvatures across the defect.
And why do you only have disk and cylinder? Where did this portion of hyperbolic cylinder come in?
No, so as I'll explain, in order to extract the matrix elements, it is sufficient to compute the correlation functions of this defect on the sphere and the torus, and to construct this sphere and torus backreacted by the line defects. You can construct them by just gluing hyperbolic disk to hyperbolic cylinders. Yeah, well, this point is going to be clear as I go on. Yeah.
Okay, thanks.
Okay, so the simplest observable that you can compute using this defect is the one-point function of the defect on the sphere, which is sometimes called the defect G function. So this is a sphere where I've inserted a defect along the equator. So I've inserted this line defect along the equator of the sphere. So I want to so this defect backreacts on the sphere. So I want to construct the resulting backreacted geometry. So the way I can do that is by gluing to hyperbolic disks, portions of hyperbolic disks across the defect. So you can think of this geometry basically as taking two hyperbolic disks and then gluing them across this defect. So let's say I have this defect inserted at some location on the disk. And then what I'm doing is I am gluing the interior. So the shaded region is the interior. So I'm gluing these two interiors across this defect. So the defect is identified, and so the interiors correspond to the two portions above and below the defect in this figure. So since the hyperbolic metric on a disk is known, we can easily construct the Liouville solution corresponding to this one-point function. So I have written down this Liouville solution in a particular coordinate system, which is nice to work with, where I have mapped the disk to a cylinder, to a semi-infinite cylinder. So in the cylinder frame, the defect is at y equal to 0. And so this is y greater than 0, and this is y less than 0. And r is like the radius of the defect. So you can construct the Liouville solution in this way. The Liouville solution can be written down in closed form. And you can extract this this function a. So a is just a constant which is dependent on the mass and the radius of the defect by this relation. And you can determine this this parameter a by solving this jump condition on the extrinsic curvature. Okay. So if you plug in this Liouville solution into this Liouville action here, you can compute the one-point function of the defect in the semi-classical limit, and it takes a nice closed form as I've written here. So let me explain a little bit about this form of the one-point function. Okay, so since this defect is non-conformal, it triggers an RG flow on the defect, and it would be interesting to understand what happens along the flow to the IR. So that's the typical question that we are interested in when we study an RG flow. So one interesting observation is the defect entropy, which is defined in terms of this one-point function in the following way. So this defect entropy is, you can think of it just as a measure of the number of degrees of freedom on the defect. So this quantity decreases monotonically along the flow, just like what you would expect in a usual defect RG flow. So the number of degrees, it's like the number of degrees of freedom on the defect are decreasing monotonically as you flow to the IR. And to get some more intuition about this, so let us probe this defect and see whether see what its nature is as you flow to the IR. Okay, so to probe this defect, note that the Liouville solution that we have just written down here, in the planar limit, that is when the mass times the radius is very large as compared to 1, takes a much simpler form. It takes this particular form. So in this planar limit, you basically have a defect in a plane, and the defect is along the real axis, and this is y greater than 0, and this is y less than 0, and the defect is at y equal to 0. So as you can see from the Liouville solution, if you probe the defect at some, so there is a characteristic width of the defect set by the inverse mass. So this region that I've shaded has a characteristic width of set by the mass of the defect. So the width of this region is like 1 over the mass. And if you probe the defect, say using a local operator, far away from the defect, like if you're very far away compared to this inverse mass, so you can basically ignore this term, these terms, and it appears that the defect is conformal. So this is one argument that the defect flows to a conformal defect in the infrared. I mean, the reason why this, sorry, there was a question.
Sorry, Jeevan, before we continue, could you please elaborate a bit on a action that you wrote before? There is like a kind of singularity when the product, when R times R is equal to 2, slightly below, when you have an expression for action. So yeah, so here, for example, you see that there is a singularity when the product of M times R is equal to 2. Could you explain a bit what does it mean or something else?
Sure, yeah, okay. So the reason why you observe this singularity is because I am evaluating the Liouville action on a saddle. and this saddle is required to be hyperbolic. So for the, and we know that on the sphere topology, there is no hyperbolic metric unless you introduce some heavy matter. So this condition that MR is greater than 2 is like a Gauss-Bonnet constraint that is required to put a hyperbolic metric on the sphere in the presence of a line defect. In other words, the line defect should be sufficiently massive for it to produce a hyperbolic metric on the sphere. So that is the meaning of the singularity.
Yeah, thank you.
In this classical action, you just added the field phi, right, to the action?
Yeah, correct.
But in 2D, we normally say that phi is not a good field and it has logarithmic correlations.
Yeah,
So
exactly. So that's why it's not like a conventional defect RG flow. So usually when you study a defect RG flow, you integrate, say, a relevant operator along some curve. But the Liouville field is not really a relevant operator. So yeah, so in that sense, it's sort of distinct from the usual defect RG flows that we are familiar with. Yeah. I mean, for instance, maybe you could think of other types of defects where you integrate some function of the Liouville field, say like e to the phi maybe. Maybe those are more reasonable. But yeah, for purposes of this talk, like I'm interested in this particular defect.
Yeah, I was just speculating whether because you just put phi, whether the quantum theory would have problems to be defined in this case.
Oh.
Because because of logarithmic correlations of phi and so on. So classically, it's okay, but
well, but even in the quantum theory, I have a well-defined expression for this line defect, right? It's just a continuous product of Liouville vertex operators. So this expression is exact. So I'm just inserting this this product of local operators into the Liouville path integral.
I'm not sure. With finite little n, it's okay, but you're taking little n to infinity, and that limit, I'm not sure, right? Because that exponential only comes in that limit. So I agree with you that as when little n is finite, you will have some good operator that you're putting.
No, little n is always infinite because I'm having like whether I'm working in the classical theory or not, little n is always infinite.
Little n is always infinite?
Yeah. Because I want to create a line defect from local operators, right? So I need like infinitely many local operators.
So that's what I'm saying. So
yeah,
this infinite n limit, this product may not be well defined, right? From what you were saying. I agree that this V operator is well defined as a single operator, and a product of 2 of them is okay. Product of 3 of them is okay. A product of infinite number of them might not be okay.
But why is that? Like why would it not be okay?
Well, you'll have to probably renormalize and all that, right? Because you're bringing the operators closer and closer to each other, and there are infinite number of them. So a priori, it's not clear that this infinite product is well defined.
I see.
Right? Because anyway, that's just a side comment. It's not really relevant for what you were saying, but I was just wondering because you put the phi in the action, and normally in 2D, we don't put the scalar field itself in the action.
Correct. Yeah, I mean, I don't have any useful comments about the quantum theory, but yeah, as such, I can't really comment on whether this makes sense in the quantum theory.
Sorry, but I guess I guess we have to. I mean, small n should be infinite anyway, because it could be like this formula could be considered as discretization of this integral over some curve. So since it's discretization, like small n should be equal, should be infinite anyway. So we cannot consider finite n, because like this is just a discretization of such integral, which is in definition of the defect, as far as I understood.
Yeah, that's right. N is always infinite. We are not considering finite n. Like the question is about, I guess, like if you go to the quantum theory, is this infinite product of local operators well defined or not? So that's the question.
Yeah, probably. Okay. Another comment is, as far as I remember, such correlators on infinite number of operators, they were considered by Zoner at some article. I don't really remember, but there were some results on like these correlators of infinite primary operators. So I mean, maybe.
Yeah, I think you're talking about this paper called Black Hole Collapse in the
Yes,
1-hour
yes,
CFT.
exactly.
Yeah. So this is actually the same setup. I'm going to derive the dynamics of those defects using the Liouville defect. So actually, it's the same setup. I'm going to describe that setup soon. Yeah. So because the line defect that in the CFT is the same as the product of operators that they consider. And yeah, that seems to be well defined, but I don't know if there are some problems in the quantum theory. Yeah. Okay, as I was mentioning, I provided some evidence that this defect flows to a perfectly reflecting conformal defect in the IR. Okay, so one can similarly compute other correlation functions. For instance, one can compute this 2-point function on the sphere. We computed the 1-point function, and we can similarly compute the 2-point function. So the way to compute the 2-point function is by computing the classical Liouville action on the geometry, which is shown here, obtained by gluing two hyperbolic disks to a hyperbolic cylinder. So basically what I want to, the setup that I have is a sphere with 2 line defects. And I want to construct the hyperbolic geometry that is obtained by the back reaction of these 2 line defects on the sphere. And the claim is that that geometry looks like this, where I just take a finite hyperbolic cylinder. So this is a finite hyperbolic cylinder. And I cap it off by 2 disks. Okay, so one can write down the Liouville solution on this surface, because we know the Liouville solution on a hyperbolic cylinder as well as we know the Liouville solution on a disk. So all you have to do is you have to glue these solutions together and solve the gluing condition. So that's all I'm doing. I won't be explaining the details of the solution in the interest of time. But if you're interested, we can discuss. Okay. So as I said, the goal is to derive the matrix elements of this defect between weights h and h prime. So that is the goal. And the way we are achieving that goal is by computing the correlation functions and then extracting the matrix elements using those correlation functions. Okay, so we can actually derive these matrix elements by noting that the thermal 2-point function of the Liouville of this defect, which is the 2-point function on the torus, has this following form. So what I want to compute is the 2-point function of this line defect at finite temperature, and that by definition is the right hand side. And now I can expand this right hand side by inserting a complete set of states, and then I get the second line. Now you can see that from the second line that this 2-point function is sensitive to the mod squared of this matrix elements. So what I can do is I can compute the Liouville action corresponding to this 2-point function, and then from the saddle I can just extract this matrix elements. So that is the strategy that that I'm going to use to extract this matrix elements. Okay, so parameterizing these matrix elements or structure constants by the following form at in the semi-classical limit. So I'm expressing the mod squared of this matrix elements in terms of the smooth functions of gamma and gamma prime. So gamma is just a proxy for conformal weights. It's just more convenient to work with gammas instead of h's in the semi-classical limit. And this function CL can be extracted using the Liouville action, and it takes a nice closed form as given here. So this is the analog of the DOCC structure constants for for the line defects that we have considered. So as you can see, this is a function which is symmetric in the two weights, gamma and gamma prime, and it is also dependent on the mass of the defect.
So just one question. So it seems like it has a finite limit as gamma goes to gamma prime. Is that right? If gamma was equal to gamma prime, then it's still okay.
Yes, it's okay. There's no problem. Yeah.
Could you have tried to calculate the single L sigma between two H's just using a sphere with one operator at North Pole, one operator at South Pole, and this defect on the equator?
Yes, one can also do that. Like for instance, if you have like local operators which are like conical defects, so you can extend this formula to operators below the threshold.
Okay, yeah.
Yeah.
And then it would agree with the same formula? Or?
It would agree. Yes, we have checked that. Yeah. I mean, you have to be very careful with the analytic continuations and stuff, but yeah, because there are some branch cuts and everything. Like, but like all of them are governed by all of the different regimes are governed by the same universal asymptotic function. So that is exactly analogous to the case for local operators. Okay. So this is a technical point. So I'll just go over it very quickly. So I have extracted the modulus of the matrix elements, but these matrix elements could have phases as well. So one way to extract the phases in the matrix elements is to compute the one-point function of the line defect on the annulus with ZZ boundaries. Because the one-point function of the line defect on an annulus with ZZ boundaries takes this form. And when you expand this using a complete set of states, you can see that it is sensitive to the matrix element and not its modulus, and not just its modulus. So without going into
Sorry to interrupt.
Yeah.
So here the boundary conditions are the boundary conditions with n equals m equals 1. Yeah. Because
yeah. The most
the most general.
The most general ZZ boundary condition. The 1,
okay.
1, I think. Yeah.
Okay. Okay. Thanks.
Yeah. Okay. So it turns out that the phases in these matrix elements are just given by a product of Liouville reflection amplitudes associated with the external weights H and H prime. In other words, the full matrix element is given by reflection phases times the modulus which we have extracted previously. So this is the result. Okay, so next I'll go on quickly to line defects in holographic 2D CFT. Are there any questions till this point?
No, I think you can go on. Yeah.
By the way, I just wanted to make a comment on time. We usually can go up to like 90 minutes or slightly more. So there's like maybe half an hour or something.
Oh, really? It's a 90-minute. Okay, great. Yeah.
Already been going on for 1 hour, so maybe like 7:05, so maybe 25 minutes or something is okay.
Oh, that's great. Then maybe I can go a little bit slower. Okay, then maybe like there's time for some questions if people have some questions. Okay. Okay, so far we have discussed line defects in Liouville CFT. So now we want to use this structure constant that we derived using line defects in Liouville CFT to derive the Cardy formula for corresponding line defects in a large C CFT. Okay, so yeah, as I said, we want to use these results to derive a Cardy formula that governs the universal asymptotics of the matrix elements of corresponding line defects in large C CFT. So, so the line defects in this large C CFT are also expressed as a continuous product of local primary operators. Yeah, so this is the same setup that was considered in the Hartmann Sonner et al. Paper that was just mentioned previously. So they considered I mean, they didn't use the language of line defects, but they considered this infinite product of local primary operators in a CFT. Okay. So there is a particular type of scaling that we want to take. I mean, it's not necessary that we need to scale n and h. H is the weight of each of the local operators. Okay, so one way to take the scaling is both n and h scale as square root c. Although that is strictly not necessary, but what is necessary is the following: that nh over c is order 1. In other words, n times h scales with c, and this combination this combination 12 nh over c is the mass of this defect, and it also turns out to correspond to the mass of this Liouville defect that we considered. And when I discuss the 3D gravity interpretation of these results, this turns out to be the mass of the shell that is created by this line defect. So just jumping ahead a little bit. So this line defect sources a thin shell of dust in 3D gravity. And you can think of this M as the gravitational mass of this shell. Okay, so specifically now we want to show that at high energies, the matrix elements of the defect are random with variance set by the smooth function that we want to determine. Okay, so recall that for local operators, this function C0, which was governing the universal asymptotics of heavy operators, was the fusion kernel that transforms the identity block in one channel and expands it using dual channel conformal blocks. So we are going to do the same trick here. So it turns out that C0D is also a fusion kernel that transforms the identity block, but now for line defects, into the dual channel conformal blocks. Okay, so so the question is, what do you mean by the identity block for line defects? So recall that the identity block mod squared is a contribution to the 2-point function of the line defect, and it's a particular contribution that is defined as follows. So let me carefully explain what the identity block means. So let's say we are on a sphere, and I'm drawing the sphere in this way in the cylinder frame, where these two vertical black lines are identified. And in this figure, I'm inserting the line defects at insertions minus tau naught and plus tau naught. So this is a path integral that computes the 2-point function of the line defect in a 2D CFT. And now I define the identity block by saying that when I cut the path integral around any rectangular cut of this form, which intersects the two defects at 4 points in a vertical fashion, that there is an identity running in this channel. So this cut could be any rectangular cut that intersects this defect, this pair of defects at 4 points. Like for instance, you would consider some other cut like this through and I'm defining the identity block such that I cut the path integral around any of these cuts, and I have an identity running in this channel. So that's how the identity block is defined. Okay, so it nicely turns out that this identity block is can actually be computed using the Liouville correlator of the Liouville defect on the disk with the ZZ boundary condition. So let me say what that means. So the identity block for the CFT defect turns out to be proportional to the 1-point function of the Liouville defect on a disk with ZZ brane. So this is the identity block for the CFT defect. So this is the base. This is the reason why you can use Liouville CFT to derive the Cardy formula in a compact CFT. So this is the underlying reason. So this applies not just to line defects but also for local operators. So you can compute the identity block contribution for local operators in a compact CFT using appropriate ZZ correlator in Liouville CFT.
I didn't quite understand your projection onto the identity block and what this rectangle is doing. Are you saying that this rectangle is like a deformation of a sphere, and inside that sphere, using the state operator correspondence, you want the identity, or what exactly?
You mean this dash
by cutting out this rectangle and having identity exactly?
Yeah, so let me explain for local operators first, and then maybe it will become clearer. So let's say I want to compute the identity block for the 4-point identity block on the sphere. So these are two local operators, O1, O2, O1, O2. Okay. So how is the identity block defined? So it is defined by inserting an identity around this curve, around any curve that surrounds these pairs of identical operators.
Mm-hmm.
So this is familiar from local operators, right?
Yeah.
So now I'm just extending that to line defects. So this particular line defect is like a infinite product of local operators. So instead of like 2 local operators, I have like many of them. So I'm just inserting identity around every pair of identical local operators.
Okay, so basically, kind of you're doing the path integral on the inside of the rectangle and projecting to the identity on the surface of the rectangle.
Yeah, I think that's one way of saying it. Yeah, okay. Yeah.
Okay, thanks.
Yeah.
May I have another question?
Yeah.
So this identity block contribution is closely related to your choice of ZZ boundary conditions. Like if you choose another, for example, physicity conditions, it wouldn't be true.
No, it won't be true. It's because the ZZ state is such that in the boundary channel, there's only the identity running.
Yes, exactly.
So that feature is not true if you change the boundary condition to like FZZT or any other. Yeah.
Yeah. Okay. Thanks.
Right-hand figure is not supposed to be in the general CFT, right? That's a Liouville.
No, this is in Liouville CFT. So the left-hand side is in general CFT, the right-hand side is in Liouville CFT.
Okay, and you're just making the statement analogous to the first one that this L sigma matrix elements appear as crossing kernel in this general CFT.
Exactly. Yeah, that's the point. Yeah, that's. Okay, so that was for the sphere. So similarly, it's you can also extend it to the torus. So like suppose I want to compute the identity block for the line defect on the torus. So that particular identity block is a contribution to the thermal two-point function of the line defect. And again, it is defined by a similar path integral where you insert the identity around appropriate channels. But now the basic upshot is that the identity block contribution on the torus is proportional to the one-point function of the Liouville defect on the annulus. So in the previous slide, I explained that the identity block on the sphere was proportional to the one-point function of the Liouville defect on the disk, and now on the identity block on the torus is proportional to the one-point function on the annulus. Okay, so these important observations suggest that when you expand both of them by in the dual channel, you can see that C0D, which is the fusion kernel for the identity block, is proportional to the matrix elements of the Liouville defect, which is like a fusion kernel for the annulus one-point function. Okay, so in that sense, we have basically derived this Cardy formula for line defects by just relating them to some observables in Liouville CFT. Okay, so this slides is a bit technical. I just want to point out that you can use this correspondence between relating the identity block in a CFT to a Liouville correlator to actually evaluate the identity block in the semi-classical limit. So for instance, the identity block on the sphere in the semi-classical limit exponentiates. And what we want to evaluate is this semi-classical block F0. And you can evaluate it almost in closed form because the identity block is a function of the modulus and the mass of the defect. And it takes this form where it parameterized it in terms of gamma, where gamma is an implicit function of the modulus that can be derived by solving this transcendental equation. Okay. Yes, so sigma is a complex modulus that determines the separation between the defects on the sphere and also the relative twist. So for instance, you could twist one of the defects relative to the other. In that sense, sigma is like a complex modulus that measures both the separation as well as the twist. And the identity block is a function of this complex modulus. This is interesting because as if you're familiar with the 2D CFT literature, there are hardly any closed form expressions for the conformal blocks. So this is one of the probably the few examples where you can write down an explicit form of the conformal blocks. And okay, so one can also do the same thing for the identity block on the torus, and it also takes a nice form. Okay, so that's about the 2D CFT part. And next I'll go to the 3D gravity interpretation. So, but I'll pause for a few questions. Okay. So if there are no questions, then I'll go onto the 3D gravity part. So in 3D gravity, sir, was there a question?
Maybe okay. I'll say that we have maybe about 10 minutes or so.
Yeah. I think I should be done. This is relatively quick. Yeah. Okay, so these defects in CFT source thin shells of dust particles in 3D gravity. In particular, these defects can source a black hole in 3D gravity. And so these black holes are formed by the gravitational collapse of thin shells of dust particles. And you can and this is one way to construct the black hole. So let me explain what this figure means. So on the left hand side you have the global ADS. I'm just considering an angular section of global ADS. So this the exact geometry is this figure times S1. So I'm suppressing the transverse S1 direction. So this black line corresponds to the ADS boundary. And this red line is the trajectory of the shell in global ADS. And then I'm gluing the physical region, which is this region, to a corresponding portion of a BTC black hole across the trajectory of the shell. So again, so the resulting geometry is a one-sided black hole formed by the collapse of a thin shell of dust particles in the Euclidean signature. And this geometry is parameterized by the location where you insert the defect. So you could say that you're inserting the defect, this line defect here, and you're inserting a corresponding line defect here. So this black hole is a contribution to the 2-point function of the defect. Okay, so I'll just explain the result. So it turns out that for the non-rotating black hole, which is obtained by gluing BTC to empty ADS, there's a match between the following quantities in gravity, CFT, and Liouville. So the semi-classical partition function of the black hole, which corresponds to the 2-point function of the defect, and in particular the identity block contribution to the 2-point function, and which is also given by the Liouville correlator on the disk. So this is the gravity calculation, and so this matches with the CFT calculation, which also matches with an appropriate observable in Liouville. So there is a match between the 3 quantities.
Could you just describe how this black hole was formed? So you have these two things that you glued together.
Yeah.
How do you end up getting a 2-point function? Because after you glue, there's only one defect, right? Roughly speaking.
No, so on the boundary there, I'm inserting a defect one defect which sources a shell that propagates through the bulk like this, and then gets annihilated at another defect.
Sorry, where are the boundaries here? Could you just maybe draw?
So this is the ADS boundary. Actually, let me draw a better picture. So let's say the boundary is a plane, and then I have 2 defects, d sigma and a corresponding defect here.
Mm-hmm.
So I want to describe the gravitational contribution that computes this 2-point function. So what I do is I just fill in this boundary condition with an appropriate bulk geometry. So the geometry can be described as follows. So these line defects source a thin shell of dust. So the dust propagates, the dust shell propagates through the bulk and gets annihilated at the other defect. So this is the black hole geometry, which is obtained by filling in this boundary condition with the appropriate 3-dimensional geometry.
Thanks. So the defects are like localized in the left figure at tau naught and minus tau naught.
Exactly. So the defects are inserted at minus tau naught and tau naught. Yeah.
Okay. Thanks.
Okay. So this correspondence also extends for a rotating black hole. So you can construct a rotating black hole by gluing a rotating BTC solution to empty ADS. And then we have the following match. So the rotating black hole partition function is a contribution to the twisted 2-point function of the line defect, where I insert this rotation generator that twists one of the defects relative to the other. And that again is given by the identity block contribution, but now evaluated at a complex modulus. Okay, so that was at the level of the black holes, which are single boundary solutions. But what about multi-boundary solutions like wormholes? So it turns out that the Cardy formula for the CFT defect, that is C0D, is reproduced by the partition function of a corresponding of a two-boundary wormhole in 3D gravity. So this is exactly analogous to the case for local operators, where the function C0 was reproduced by the partition function on an appropriate wormhole. So in this case, let me explain the two-boundary wormhole. So the boundaries are so the two boundaries are spheres with a line defect d sigma inserted along the equator of the spheres, and then there are world lines of local operators propagating through the bulk. So this is a contribution to the matrix element square. So this wormhole gives a contribution to the square of this matrix element of the defect, and its partition function agrees with this C0D that we just derived. And yeah, I will not go into details, but one can show that one can compute the classical action of this wormhole geometry and show that it reduces to 2 copies of Liouville action. So that's how the correspondence is set up, because this is how 3D gravity reduces to 2 copies of Liouville, and also we showed how CFT results can be reproduced using Liouville. So hence the correspondence is established between the three gravity, Liouville, and CFT. Okay, in the interest of time, I'll just mention that you can also compute the partition functions of multi-boundary wormholes. And again, they match with the Gaussian averages of the defect matrix elements with the variance set by this function C0D. So this was again analogous to the case of local operators. Okay. So far in the talk, I've always whenever I've talked about averages, I never clearly mentioned about like what exactly am I averaging over in the ensemble, right? So one way to interpret the formal averages described in the talk is in terms of averages over coupling constants. For example, if there was a marginal scalar in the spectrum of the CFT, one could imagine averaging over the marginal couplings. So you could average over small windows around the marginal couplings and then interpret the formal averages that I've described in terms of these, in terms of more, in terms of less abstract averaging over marginal couplings. So the question is there a precision test for such an average? Meaning that what do the averages give us when the couplings in the two theories are slightly different? So suppose I want to compute 2 copy observables in CFTs, but now the CFTs are slightly different from each other, like in the sense that they have different marginal couplings. So interestingly, this question can be answered by constructing 2-boundary wormhole solutions, which are locally described by the Janus domain wall solution of Einstein-Dilaton gravity. So consider this particular 2-boundary wormhole solution that we just visited here, that was computing the variance. But now, in addition, there is a scalar field that propagates through this wormhole, and such that the asymptotic values of the scalar field on the two boundaries are different. So these asymptotic values of the scalar field correspond to the marginal couplings in the 2 copies of the CFT. So this wormhole computes average between observables in 2 different CFTs because they have different marginal couplings. And one can actually compute the action of this wormhole, and the action turns out to be take a particularly nice form. So you have the familiar variance function C0D, and in addition, there is a term which depends on the difference in marginal couplings. And so these eta i's are just the conical deficit angles corresponding to the local operators I and j, and m is the mass of the defect. And this is this gives a covariance between the matrix elements of the defect in marginally deformed CFTs. Okay, so this formula is very interesting because for the following reason. Let's say we take the weights to be above the black hole threshold, then it turns out that the covariance takes a more universal form. So suppose these weights are above the black hole threshold. Then if you observe this term, which depends on the difference in the marginal couplings, it only depends on the mass of the defect and is independent of the weights of the operators. And importantly, you see that this argument of the exponent is negative, which means that the covariance decreases monotonically as the difference in marginal couplings increases. I mean, this is consistent with our intuition because we would expect that if you have two very different CFTs, then they should have less correlation between them. And that is what we are observing in this simple setup, that the covariance decreases monotonically as the difference in marginal couplings increases. Okay, so that comes to the end of my talk. I've basically described a simple example of an average holographic duality where I showed that the statistics of black holes formed by the collapse of gravitational collapse of thin shells of dust particles is governed by the universal dynamics of a class of line defects in CFT. And we established this correspondence between various quantities in gravity, CFT, and Liouville CFT. So let me quickly take like a couple of minutes to explain some future directions. So it would be interesting to, so I described non-conformal defects in Liouville CFT, and which also correspond to non-conformal defects in a compact CFT. So it would be interesting to understand better the RG flows on such defects and also understand the gravitational interpretation of such an RG flow. Like, because these solutions are describing black holes in the bulk. So it would be interesting to understand what the RG flow on the defect would do to the black hole in the bulk. Okay, so in the talk, I only talked about conformal, non-conformal defects in Liouville CFT, but it would be interesting to derive the dynamics of conformal defects in Liouville CFT using the similar approaches, and also if they correspond to some universal dynamics of conformal defects in 2D CFT. That would be really interesting because conformal defects have numerous applications, and people are interested in it for a variety of reasons. And similarly, it would be interesting to study the holographic interpretation of conformal defects with source domain walls in 3D gravity. So one can indirectly compute the structure constants of such defects holographically from the on-shell action of black hole sourced by domain walls. And interestingly, it turns out this such domain walls, dual to conformal defects, also affect the statistics of local operators. So it seems to suggest that these domain walls are also affecting the ETH of local operators in 2D CFT. In other words, the extended operators in CFT also seem to affect the statistics of local operators. So that's the, yeah, I won't be able to get into the details, but yeah, it would be interesting to understand this. Yeah, this is, that's all I wanted to say. Thank you.
Yeah, thanks for a very nice talk. We already had a lot of questions. Are there any quick or urgent questions?
Just ask one relating to your point number 2. So, I mean, in a general irrational CFT, we don't even know what the conformal defects are, right? Like the analog of these Cardy states are not known. So
exactly. Yeah. It would
in mind with this.
Sorry.
And what's the idea? Like, how would you? What class of conformal defects would you consider in a C bigger than 1 irrational CFT?
Well, true. I think it's an important. It's an important point that first one needs to understand. One needs to come up with some examples of conformal defects in 2D CFT. But what I was trying to suggest is that even for this case of a non-conformal defect, we only assumed its existence in a CFT. So if you just assume its existence, then you can derive its dynamics using Liouville CFT. So that's all I wanted to suggest. Yeah, but one needs to actually find some examples. But But irrespective of whether there are examples, like you can probably solve this problem more abstractly using Liouville CFT.
I guess you could do some crossing kernel ideas even there, just assuming.
Yeah.
Okay, yeah, makes sense.
Maybe I can ask a very quick question. Do you have any comments about generalizations to higher dimensions? Like there have been results from the gravity side.
Yeah.
Okay.
Well, yeah. So on the CFT side, it's largely an open question to derive the statistics of these shells in higher dimensions. But on the gravity side, it's straightforward to extend these calculations to higher dimensions as well. Like you can, yeah. Okay, I won't get into these details. But I had some extra slides. But but I think promising direction in that to reproduce the statistics from CFT would be using this framework of thermal effective field theory. That has been recently used by David Simmons-Duffin and collaborators to derive a Cardy formula for local operators in higher dimensions.
Right.
So I would think that that is the most natural framework to use. If you want to try to derive these statistics in higher dimensions.
Okay. Yeah. Thank you. If there are no further questions, let's thank Jeevan again for the very nice talk.
Thank you.
Thank you for the talk.
Yeah, thanks.
Yeah, thanks a lot. So we can end the official thing